Hello, my name is Karkada Shashank Hegde. I'm a PhD student at the University of Southern California. In this work, we answer the question, how do we learn smaller control policies for robotic control in locomotion and manipulation? Having a smaller control policy provides benefits such as reduced latency and lower onboard memory requirements. To analyze the dependency of performance on size and architecture, we run Soft Actor Critic, a popular reinforcement learning algorithm with different architectures on the half cheetah environment. We see that larger policies generally perform well, but finding a small policy is not straightforward. For example, a policy with hidden layers 16:8, 32:8 performs better than 40:20, even though it has fewer parameters. Thus, finding a smaller policy is not straightforward, and repeated experimentation can be time consuming. Therefore, we describe a method which provides a large number of working policies, each one unique in architecture and each one performing almost as good as the optimum policy. Then, during deployment, the researcher can choose an architecture that conforms to the required hardware/latency constraints. For an existing actor critic of policy RL algorithm, we replace the vanilla actor policy network with the graph hyperpolicy network. This GHP network estimates the weights of a control policy network that optimizes the Q value function of the actions taken by the control policies. The GHP takes as input the graph representation of the policy networks. It then encodes each node of the graph using a linear encoder. Then, a gated graph neural network performs message passing between adjacent nodes in the graph. A Mac-shaped decoder then converts the encoded nodes into a matrix of size 512 cross 512. We then tile or crop this matrix for each node to fit into each layer of the control policy. With meta batching, we can estimate parameters for multiple control policies at the same time. The parameter estimation of the GHP is optimized by using the Q value function. On various locomotion and manipulation tasks, our method trains thousands of control policies with comparable sample complexity of a single architecture MLP trained using vanilla of policy RL. For locomotion, we use soft actor critic, and for manipulation, we use deep deterministic policy gradients with hindsight experience replay, with the same hyperparameters as the baseline. On analyzing the result, we see that we can find architectures nearly 1/100th the size of the baseline 256 architecture that achieves at least 90% performance of that baseline. We shall call these 90% architectures. We first compare the performance of the best architecture and the baseline and see that our method does not sacrifice performance while training more policies. We then identify the smallest architectures that achieve at least 90% max performance. Identifying these 90% architectures before training the GHP would not have been possible. But on training these architecture policies from using vanilla of policy RL, we see that our method performs as good as this baseline. By visualizing the rollouts, we see that these tiny MLPs do complete the locomotion task as expected. Similar results are also seen in the manipulation environments. Identifying these 90% architectures can be time consuming, as we have to estimate and evaluate every architecture possible. To reduce this effort, we use lossless memory dimension of an MLP. On evaluating the performance of every architecture, we see that the performance is not strongly correlated with the number of parameters, but it is highly correlated with the lossless memory dimension of the multilayer perceptron. Therefore, we propose that for a given parameter count cutoff, the architecture that maximizes the DLM maximizes the performance. We empirically show that by sampling random parameter count cutoffs between 1,000 and 10,000, 100,000, architectures that maximize this DLM perform better than the largest network that satisfied the parameter cutoff and is almost as good as the best performing policy. In conclusion, we propose a solution to architecture search that is efficient in number of training samples collected. And this architecture search is for robotic control policies. Our method generalizes to any off-policy RL algorithm. And finally, we analyze the DLM of a neural network as an effective predictor of eventual network performance. Thank you.